Hi, in a previous video I did a little soldering iron shootout of sorts between this new model Weller WE1010 and the venerable Hakko FX-888D here, and both of these irons are like $100 class irons, and I came to the conclusion that they're, six of one, half dozen the other. There's not really a huge amount of difference between them. And Lewis Rossman, fellow video blogger, you should subscribe to his channel if you haven't seen it. It's excellent. He does repair videos and other advice and stuff, and he basically did a response video to this saying, well, these are old technology and he doesn't know why they're still on sale, and you basically, kind of paraphrasing, you can go watch the video, I'll link it in down below for yourself, then they're basically pretty crap and you shouldn't buy them. His advice was he would rather have a new technology soldering iron, even if it's a rip-off one. In his particular example, he was referring to basically the sort of more professional upgrade to the Hakko 888 here, and that was the FX-951. And that FX-951, very good iron, of course, very capable, and it does use the new technology, as we'll talk about. But it's like a $250 plus class iron. So, a completely different price bracket to these older technology irons, so to speak. But you can actually buy rip-off, clones on eBay or Alibaba or wherever of that Hakko FX-951, and they're about the same price as these. So about, $100 odd or something like that. So Lewis's argument is that he would rather have one of the new technology irons, even if it's a rip-off, compared to a genuine one of these, like using the older technology for the same price. And it's an interesting argument. I recommend you watch his video down below. So this video is going to kind of be a response to that response, I guess, but it's a standalone video basically looking at the difference between an old technology iron like the FX-888D or the Weller here and a new technology iron, this JBC CD-2B series iron. But this is a very expensive iron. I think it's like $500 or something like that. Now, when we're talking about the difference between old and new technology, I'm using the quote marks, even though it's, it's technically correct. The difference is not so much in the station itself or even the power available in the station. Like, this is a 65 watt capable iron. I believe the JBC happens to be like 130 watts peak power. So it's more powerful, but that's not really what we're talking about here. The difference is in the tips are the same, basically, but the way it actually transfers the heat to these tips and measures it. Yes, they are turned off. Otherwise, I'd be smelling something quite bad. So first of all, let's look at the old style soldering iron technology, which has been around from day dot, and you can still buy it. And in my opinion, they are still very useful irons, as we'll get into. We'll do some demonstrations later. But if you take off the sleeve here, you can see that there is a ceramic heater element in here like this. And in terms of the Hakko, I don't actually know where the actual temperature sensor itself is. It may actually be embedded in the ceramic element or whatever. But basically, these old technology ones, the tip is just that. It is just the tip. Now, you can get poorly designed tips, you can get really well-designed tips, and there will be thermal performance differences between them and between manufacturers. But the point is that they're basically, the tip is decoupled from, physically separate from the heating element and the temperature sensor. So you've basically got extra thermal resistance in there because you've got to rely on the contact and maybe some air, because that's a little bit loosey-goosey, So there's not as good a contact between the element itself. So when the element heats up, there's going to be some lag between that element heating up and the tip actually getting hot. And, well, that's not a great thing when you're soldering, because when you apply your solder down onto the copper, and, if you've got a large heatsink, you're doing a large ground plane or a large thermal mass like that, then it can suck away a lot of the heat. And all soldering irons, regardless of whether they're new or old technology, will actually have a drop in temperature. And I'll explain that in a minute. But these newer technology irons, not just this JBC, but the Hakko FX-951 and all of the other high-end ones, basically use a different system. The tip is not just the tip anymore. The tip actually contains the heating element itself up there in there somewhere. I don't know if I can find like a cutaway drawing or something, I'll find one. But the element will be integrated into the tip as well as the temperature sensor. And the way you can tell is because, look, it's got electrical contacts on here. And sure enough, you can actually measure that. There we go. There's like presumably the coil resistance. I don't know which way around the contacts go and which one's the thermocouple element and all that. But basically, the element and the thermocouple are built into the tip. Now, you don't really have to be a thermal expert to understand that this is going to be a more responsive technology. When you apply power to that heating element, the tip is going to heat up quicker and faster, assuming all things are equal amount of power, equal amount of element and everything else, because there is direct coupling inside here. They've specifically engineered and designed and made these so that they have better thermal performance than just the ceramic heating element and, well, heat will get through to the tip eventually kind of thing. So they're the two differences between the old and the new technology, and there is absolutely no doubt at all that the new technology is better. If you can afford it, get an integrated element tip soldering iron like this one, for want of a better word. I don't know, that'll do. But are these old style ones, I don't know the exact terms that Lewis used, but he basically said, they're hopeless, right? Don't buy them. You're better off buying a clone version of one of these, even if it's, real crap quality. You're better off doing this. And, well, there's some merit in his argument because, of course, Lewis does mostly, he's a professional repair tech. So he repairs motherboards and all sorts of other, consumer electronics that have very large ground planes on them and lots of very delicate surface mount stuff on those ground planes and things like that. So, if you're doing professional electronics repair and maybe assembly work like that, just get one of these. If you can afford it, get a direct heat iron. So there's absolutely no argument there. But really the question for this video is that, are these old style ones any good? Are they still useful? And I reckon the answer is yes. And I'll demonstrate it. You can still do an awful lot, if not most of the stuff you can do with an older style iron like this. Personally, I'm going to be using my JBC in the lab here if I have a choice, because yes, it is better performance, as you will see. All right, so let's see one of the advantages of these direct heat irons, but bear in mind this one is 130 watts peak compared to 65 watt iron here. But if we switch them on, then we'll actually be able to see how quickly they heat up. And this one, well, actually, sorry, that's that's wrong. Got to wait for this thing to power up, right? Anyway, well, it's basically there. The thing with this one, it has like an auto sleep mode, so it actually sleeps when you put it into the stand like this, and the actual temperature is 225. It's actually dropping, but when you pick it up, it can actually heat up within, I believe the spec for this is 3 seconds, or 2 seconds or something like that. 2 or 3 seconds, very typical to have these heat up. So you can actually have an auto detect stand like this, and which cools the iron down, and as soon as you pick it up, it boom, see how it's got power on the screen there. It shows the amount of power that it's actually driving into this, and if we put it on here, we can actually see that power bar go up, right? It's now delivering 100% power like that, and it's dropping. You'll notice that this is, well, look at that, 120. This one goes right down. Whereas, of course, you've seen this in the previous video, these more traditional ones, they take a long time to heat up. That's going to take quite a while to get to 260, so you wouldn't have a setback mode for one of these more traditional irons, because it just takes too long to actually heat these things up. But these aren't magic, of course. They're going to drop. If you actually look at the specs for this JBC iron, it says it drops typically 35 degrees C temperature, tip temperature, and it says, well, competing ions, I guess they're referring to these older technology ones here, the non-direct heat type, then they can be up to 70 degrees C temperature drop. But let's actually do the sponge test. I've set this to 260. You can see there's a little bit of overshoot there, and we're back. We're good. Let's actually put it on the tip. Look at that. So that sensing is, the sensor's not terrific, is it? Is it genuinely actually going down to 85 degrees Celsius? But if it is, look at how quickly it recovers, right? Bang. It's already back. It overshot to 280, but it's back, you know, up, ready to do the next joint. And that's the advantage of these things. These things are very powerful in that respect, in that you can do lots of joints very quickly. If you want to do a joint every second or two, you probably should have one of these. This may not cut it if you do that. So that temperature drop can be a real big deal. It can make or break A, what temperature you solder at, and B, what types of devices you're able to solder. If you're looking at a reasonably, you know, a large copper ground plane like this, it's going to absorb or sink more heat from the tip of the soldering iron than a soldering a little, you know, 0603 surface mount component with a tiny little pad. Or if you're soldering the big tab of a big power transistor or something, that will act as a big heatsink. And this also has to do with the melting point temperature of your solder, and we won't go into the metallurgical stuff of that. That's a whole field in its own thing, in the plastic region, and you've got to understand all sorts of things. But suffice it to say that your lead-free solder that you know, you're supposed to use these days has a higher melting point temperature of it varies depending on the type, but this type 99C here melts at a nominal 227 degrees Celsius. And your good old lead solder, like your good old 6040 or your, you know, 6337 or your, you know, like the Savbit ones like this, these will melt at 183 degrees C. So, you know, there's a good, 45 odd degrees difference between these two. And when you're soldering your joint, you've got to factor into account that temperature drop of your tip. So let's actually just experiment with a couple of these different types, and I'll show you. So what we're going to try and do is solder onto a ground plane like this. Oh, it's not the biggest ground plane in the world, but it's a ground plane using lead-free solder that melts at a nominal 227 degrees Celsius. And we'll set both of our irons to 240 degrees. So above that, so we should find that it'll actually melt. And now I'll put some flux on there just so it activates, and let's have a look at our old school iron. Here we go. It should, the solder is actually, it will melt. There you go. It will melt because it's reached that temperature, but let's see if it'll actually do that down on the board, shall we? Here we go. No, it's not working well. Nah, it's like, stone motherless cold. Look, I mean, it's just, look at that. Hopeless, right? It's kind of, sort of just stuck there. But let's do the exact same thing with 240 degrees on the JBC here. So let's give this a whirl. One side of this tip is a bit crusty. So let's try the JBC, shall we? Let's see if it can do it at 240 degrees C. Yep, it can do it. Just, it's melting it. Yeah, it did the job. There you go. So that is the difference there between these two. With the direct heat iron, we can solder lead-free onto a ground plane at, 240 degrees C. We can go down a bit. We could drop it down to 220 and it's just not going to work at all. But we can go to a really low, safe temperature. And that's the goal of almost any soldering, is to use the lowest temperature you can that's going to do the job properly and do it in a timely manner, of course. It's no point going so low a temperature that you have to leave the iron there forever until it actually you know, melts up, because that could, leaving it longer there, could heat up the component more and stress it. So it's a bit of a trade-off, but generally speaking, you want to do it at the lowest temperature you can that gets the job done quickly enough. And in this case, this one, the direct heat iron, wins. Okay, let's try the Hakko at 260, shall we? Let's give that a whirl and see if we can get it to heat up. Come on. You can do it. No, doesn't like it. Okay, let's try it at 270, shall we? Okay, let's try it on a new section here, complete with the flux, at 270, and no, still can't do it. And if we try it at 280, I can actually get it to do the business. But once again, remember, this is a less powerful iron, 65 watts versus a 130 watts peak there. But, you know, I was able to get it at a lower temperature, but yeah, it's kind of sort of a bit hit and miss. You have to leave it there for a while, but you can see the difference. Just in case you're curious, note the Weller can't do it at 240 either. It's hopeless. And at 260 with the Weller, yeah, it's struggling. The solder's melting, but oh geez, it's not that great. And once again, you just get the JBC on there, and at nominal 240, no problems whatsoever with that. But it's a different ball game if we want to use 60-40 solder that melts at 183C. I've got all 4 irons set to 240 volts set temperature here. And let's try the Hakko. This has already got some over here. And bingo. Look at that. 240. Oh. Takes a second or two to get the heat into it, but no problems whatsoever, right? And we can do the same thing with the Weller here. 240, I haven't tried the Weller yet, but there we go. It can do a similar thing. So they can all melt, and of course the JBC is going to, I'm choking on the fumes, JBC is going to do the business, but as you can see, it's kind of like a much quicker application there. Like if I go like that, boom, that was with no flux. Let's try this with the Hakko with no flux, shall we? It's almost as good, but you can feel it stick a little bit more. But there's not much in that. Both can, like all of them, can use a low temperature of 240C with 60-40 solder onto a ground plane like that. You know, yeah, you can tell the JBC's ahead, but not as much as it is with the lead-free solder. Alright, so let's actually have some fun with the FLIR ETS320 thermal camera, which can go up to 260 degrees C. So I'll use leaded solder, and we'll use the 240 degree temperature we had before, and we'll check out the how it looks under the thermal camera, see if we can see the temperature drop. Alright, so let's do this. I'm going to use the Hakko first, and I haven't tried this yet, so let's actually, what I've got is the center point. This is the point I'm going to solder, so that's going to be, I'll put that like smack in the middle like that, so we can read the temperature up there, but also the maximum, it should tell us the maximum soldering iron temperature up there. So let's do a test. Okay, so what we need to do is actually set up the emissivity, and there's a whole list of custom materials and stuff in here, and really, like, you know, there's copper polished and all that sort of jazz, but yeah, really we're just going to have to do this by experimentation, by setting the custom value like this. I've already set it to 0.5. It was a bit over, so I'm going to set it to 0.4, and we'll give that a whirl. And because we know our temperature of our iron's pretty accurate, because we measured it the other time, 240. I'll tweak it a bit more, but yeah, we'll get it right. Okay, I'm going to call that at 0.35 emissivity 246. Doesn't matter, right? We can actually, what we want to do is we want to see the temperature drop. So we're looking in the top right corner of that and see the temperature drop. So let's try the Hakko at, there we go. So it was 240. Let's see what happens when we actually heat up our big copper here. So there we go. It's dropping by. Well, once again, it's the well, the top side of the tip, I guess you could say. So it's why is it doing? It's barely doing. It was doing it well before. There we go. There we go. See, so it hasn't dropped by a huge amount. It's dropping maybe 215 or something like that. It's not dropping by a huge amount on this particular type of copper clad. But let's see how the JBC holds up to that, shall we? Wow. Okay, it looks like we've got a very different emissivity for our JBC here. So I may have to tweak it yet again. It really, you know, there's a big difference there. Quite surprised by that. But anyway, let's tweak it again. All right, we'll run with that. I've got an emissivity of 0.75. So let's do the JBC here. You can see that, yep, it really doesn't drop by anything. But once again, this is 135 watts peak. Just remember that. So that could be all the difference in this particular case. But as you can see, it did that with basically very, well, maybe, okay, let's just say 10 degrees C drop or something like that. But you get the idea that the direct ions like these, direct heat ions, are obviously going to have a better thermal capacity than your old style ones. So let's actually just turn the Hakko up to 270, which is 30 degrees higher than the JBC. But in terms of actually doing a ground plane like this, but in terms of actually damaging a component, it's going to basically drop down to the same temperature anyway. So, you know, it's not really a problem. And there it is. You know, it's a little bit struggling a little bit. But once again, you know, you could turn it up. But there you go. Like, it's melting just fine. But of course the JBC, of course, will just do that like straight on. I don't even need to add in, like straight on at 240. So, you know, there you go. But at the end of the day, that copper's probably at, you know, a similar sort of temperature. Yeah, it's better, but it's not a huge deal, really. It still works. It gets the job done. You might have turned the heat up a little bit, but it's not enough to damage your components. And for low thermal mass components, there's going to be practically no difference between these. Really, if you're doing surface mount soldering or anything like that, there's just, like, this one's just going to do as good a job as this one. It's only when you get into the higher thermal mass components, and really, if you're doing a joint per second or something like that, it could make a difference. But overall, it's not a huge amount for just general purpose soldering. So there you go. I hope you found that interesting look at a old technology indirect heat one and a new modern direct drive one. And I completely agree with Lewis. These are better. There's absolutely no doubt about that. But these are not, I don't necessarily agree that these are, you know, crap or you shouldn't buy them. I think, you know, for $100, okay, you could argue, like Lewis said, that $100 you can buy a rip-off direct drive one, a rip-off Hakko direct drive one from the Shenzhen market, and it's crap quality inside. But he reckons, I haven't tested one, but he reckons that it works almost as good as the direct drive Hakko FX-951. Or you can spend $100 on the FX-888, this older style one, but they work okay. Yeah, you're not going to be doing high volume production soldering. If you're there just, you know, like boing, 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 you know, like an extra second or two it takes to heat up, to reheat this compared to this. If you have a look at that Hakko graph again, then yeah, you know, you have to let it, if you did 2 seconds per joint, then this one's going to do the job, and this one just may not work at all if you want 2 seconds per joint, depending on, once again, the type of solder that you use, the thermal capacity, the thermal sink capacity of the device you're trying to, the pad, your component you're trying to heat up, and all that sort of jazz. There's lots of things that go into it. But yeah, if you're doing high-speed soldering or maybe big ground planes like Lewis is doing with repairs and stuff like that on big modern motherboards and stuff like that, yeah, definitely get one of these. But these are not as crap as you might think. You can do an awful lot with these, if not most things that your regular hobbyist or enthusiast is going to encounter. So there's nothing wrong with these at all. Hope you found that interesting. If you did, please give it a big thumbs up, and as always, discuss it down below, and I'm sure everyone will. And yes, I plan on getting Pace have got a new the ADS-200 direct drive iron that they're sending me, and I'll probably get an Hakko FX-951 to compare that with and everything else. So I might do a shootout of direct drive irons. Is that the correct term? Direct heating, direct drive, integrated tip, whatever you want to call it. Anyway, it's interesting, but there's a lot of variables that go into this. As I said, the type of solder and the parts you're using, and this temperature you want to solder at, the recovery time that you want, the number of joints per second that you want to do, the maximum temperature of the component you're looking at, the not only the maximum temperature of the component, but the amount of time you can leave that heat on there. And there's just countless things. If you really want to go down the rabbit hole, you can. But yeah, if you can afford it, get one of these direct drive ones. Anyway, hope you found it interesting. Catch you next time.